Hi there and welcome back. Today we're going to look at another application of the quadratic equation, and this involves teamwork. And I'm not sure what you think of as teamwork, but the idea here is when we have several people working together to try to get a job done, and we know how long it takes, and we're trying to figure out how long would it take them to do it individually, or how long would it take them to do it together. These are really cool problems. And the most important rule of all is always use a table to organize. And there's a little bit of work that you got to kind of keep straight here. And once you understand how that works, these problems actually become pretty easy. So the big idea here, and I'll write it down, and once you see that, then you'll understand how to create the table. So this big idea that I've written down here is really the key to solving these problems. And as it says here as an example, if you take 10 hours to do a job, then the rate at which you're working is 1/10 of the job per hour. And once you get that, then solving these problems is a lot like solving problems that have to do with rate times time equals distance. And you'll see how close this is to that. So let's look at a particular example and we'll see how we can use this big idea to solve it. Okay, so read the question. We've got 3 people and we know how long it would take each of them to do a job if they worked all by themselves. And the question then is, how long will it take them to do the job if they work together? One of the interesting things about these questions is you don't always get the answer that you would suspect. So how long do you think it would take them to do it if they all worked together? And then we'll get the answer and you'll see if you're close. So as I said, we want to use a table, and I'll show you what that table looks like on all of these problems. So here's how the table begins to look. We need a row for Abby, and a row for Billy, and a row for Kathy. Now, remember I said these are a lot like rate times time equal distance, but there's a difference. So we do have rate, and look up ahead at the red note to talk about how you do the rate. And then we have time, and finally we don't have distance. But if Abby or Billy or Kathy is working at a particular rate for a particular time, then what this column is how much of the job each of them does. So let's try to write this down. It took Abby 3 hours to do the job, so she's working at the rate of 1/3 of the job per hour. Billy is 1/4 of the job per hour, and Kathy is 1/5 of the job per hour. Question is, how long does it take if they do the job together? So we'll say this is T hours, and this is T hours, and this is T hours. So Abby is working 1/3 of the job per hour for T hours. If you multiply those together, do you see what you get? You get T over 3 of the job, T over 4 of the job, T over 5 of the job. And now, here's the second really big point. When they work together, they do one job. So what that suggests is the following simple equation, that T over 3 plus T over 4 plus T over 5 is equal to one job. So we want to get rid of the fractions, multiply by the, what number would it be? It would be 60, right? And so if I do that and I keep track of things, I'm going to get 47H is equal to 60. Sorry, T is equal to 60. So T is equal to 60 over 47. A little bit more than 1 hour. That's how long it takes them to do the job together. Is that about what you guessed? Okay, so the big deal here is the way this table works, and the part that you got to get used to is that this rate times time is equal to the part of the job, and when you add together all the different parts, you get one full job. Okay, so that's the technique that'll work on all of these problems. Okay, so read this question, and again, think about it. How long do you think it would take Sally to do the job alone? Maybe 2 hours? 3 hours? Again, it always takes a little practice before you can begin to guess at these correctly. So let me set up the chart, and you set up the chart. So press pause and set up the chart the way you think it should go, and we'll see how you do. So here's how I set it up, and you might have done it differently. But we know that Sally works twice as fast as Jim. So if Jim works at J of the job per hour, then Sally works at 2J. We know that if they work together for 6 hours each, they do the whole job. Well, if Jim works at this rate for this time, this is the part of the job he does. Similarly, this is the part of the job that Sally does. And then the big deal, remember, is that together they do one job. So what that tells me is 6J plus 12J is equal to 1. Notice, not a quadratic equation here, but if we solve this, we get J is equal to 1/18 of the job per hour, and Sally is 2J, so Sally works at 2/18 of the job per hour. 2/18 is 1/9 of the job per hour. So Sally needs 9 hours. Did you guess that? Working alone. Again, it's always a little counterintuitive. Okay, we'll do one more. Okay, so this one reads a little bit differently, and you want to think about how to set this up. So the question is, how long would it take Sally to mow the lawn alone? So let's just begin with our variable. Let's let S equal number of minutes for Sally alone. Well, John takes 24 minutes more than Sally. So what that means is S plus 24 equals number of minutes for John alone. All right, so now we can set up our table. And again, let's see how well you can do at this. So press the pause button and set up the way the table should look. And let's see how you do. So check it out. How'd you do? If it takes Sally S minutes working alone, that she's working at the rate of 1/S of the job per hour. Same thing for John. They mow the lawn together in 9 minutes. So in 9 minutes, this is the part of the job that John does, the part of the job that Sally does. And we've seen a couple times now that the total is one job. So therefore, the equation is 9/S plus 24 plus 9/S is equal to 1. And how do we solve this? Okay, so this is an equation involving rational expressions, and we need to multiply both sides by the common denominator, which is S plus 24 times S. And if I do that carefully and correctly, here is what I get. So I left a lot of steps out there, but you should be able to figure out why that is true. And now if I simplify this, what I'm going to get is 9S plus 9S plus 216 is equal to S squared plus 24S. Okay, so there's a quadratic equation. This is what makes it be quadratic. And as soon as you recognize that it's a quadratic equation, you want to get everything over on one side and 0 on the other. And if I do that carefully, what I get is my final solution, which is s is equal to 12 or minus 18, and clearly minus 18 is no good. So my solution is 12 hours. So Sally needs 12 hours to mow the lawn alone. Okay, there you go. So a lot of missing steps in here. And if you're confident you can do that, fine. If you think you need some practice in solving an equation that looks like this, then by all means take some time and make sure that you can follow how I get from here to here to here. Okay? Alrighty, almost done. See you next time.